Hi everyone. In today's class, we'll discuss about properties of Z transform. In the last session, we discussed about the introduction to the Z transform. So in that we discussed definition of Z transform, then ROC, the region of convergence. Then we discussed the properties of ROC. Then we solved some basic problems. And today we'll discuss about basic properties of Z transform. And these properties, which is applicable for all the transform techniques, like Laplace transform, Fourier transform, and so on. So the properties of Z transforms are linearity, time shift, then time reversal, then differentiation in Z domain, convolution properties, and all. And by using these properties, we can solve the different type of problems, and it will be very easy if I use the property and if I apply that property in the problems. It will be very easy to solve it. And while taking inverse transform also, it is very easy, and if I know the properties, then I can solve the problems. So that is an advantage of using the properties. So we'll discuss about properties in that, properties of Z transform. The first property we'll discuss here, the linearity. So linearity property, to prove linearity property, should know the law of superposition. It states that the weighted sum of the input signal should be equal to the weighted sum of output signal. So to prove this linearity property, I have to consider more than two signals. So here I will represent in terms of two signals. I have taken the two signals as x of n and y of n. And you know that the x of n Z transform is x of z with ROC is R1, and the y of 1 Z transform is y of z with ROC R2. Then is the combination of the input signal, the weighted sum of the input signal, that is a into x of n plus b into y of n. Z transform is a into x of z plus b into y of z. So I have taken the resultant signal as c of n. So in Z transform it is c of z. With respect to the ROC will be the intersection of R1 and R2. So there are two signals are there with ROC, one is R1, other one is R2, and the ROC of the resultant signal is R1 intersection with R2. I'll explain that, we'll take that intersection and all while solving the problems. Now by using the definition of Z transform, you can write C of Z is equal to the summation over minus infinity to plus infinity C of n z to the power minus n. We know that C of n is a into x of n plus b into y of n. So I'll substitute in that equation. So summation from minus infinity to plus infinity a into x of n plus b into y of n z to the power minus n. Now I'll multiply z to the power minus n to both the terms. Therefore the integration is summation is n is from minus infinity plus infinity a into x of n z to the power minus n plus b into y of n z to the power minus n. So I'll take the constant term outside and I'll take separately both the terms I'll take separately. So a into the summation over minus infinity plus infinity x of n z to the power minus n plus b into the summation over minus infinity plus infinity y of n into z to the power minus n. Now I applied the definition of Z transform here. So the first term is a minus infinity plus infinity x of z to the power minus n can be written as x of z. Similarly, summation over minus infinity plus infinity y of z to the power minus n can be written as y of z. So therefore C of z is equal to a into x of z plus b into y of z. So this is my RHS. So I have taken the signal as a into x of n plus b into y of n. I got the output as a into x of z plus b into y of z. So the weighted sum of input should be equal to the weighted sum of output. So this is about linearity property, and now I'll take an intersection also. Suppose one example I'll consider here. Suppose x of n is alpha to the power n u of n plus beta to the power n u of minus n minus 1. So for that you'll get the answer as z by z minus c, z by z minus alpha plus z by z minus beta, and one will get with ROC as it is greater than alpha, other one will get the ROC is z less than beta. So if I'll combine it, I'll get the condition is your magnitude of z is greater than alpha, at the same time it is less than beta. So we'll get our ROC as a concentric ring. Second property we'll discuss about time shift, and this property is used to solve a differential equation. You're using this, and it is most commonly used properties while solving the problems. So here I consider input signal x of n, z transform is x of z, and then I'll take one more signal, the shifted version of x of n, that is x of n minus n naught, as y of n. So y of n is equal to x of n minus n naught, and its z transform is z to the power minus n naught into x of z. So that is equal to y of z. So y of z is equal to z to the power minus n naught into x of z. The shift in the time domain results in the multiplication by some complex term, that is z to the power minus n naught in z domain. So I will prove this. So I'll apply the definition of z transform, that is y of z is equal to the summation n over minus infinity plus infinity y of n z to the power minus n. Now what is y of n? The y of n we'll consider it as x of n minus n naught into z to the power minus n. Now I'll substitute, it is put n minus n naught is equal to m. And from that equation I'll get n is equal to m plus n naught. I'll apply the limit, the lower limit is minus infinity, so when n is minus infinity, m is also minus infinity. And n is plus infinity, m is also plus infinity. There is no change with this respect to the limit. Therefore, your summation is m over minus infinity plus infinity x of m z to the power minus m plus n naught. The next step, I'll expand it, so I'll get z to the power minus n naught, the summation of m from minus infinity plus infinity x of m z to the power minus m. And here if I use the general equation for z transform, we know that z transform of x of n is x of z, that is given by summation of n from minus infinity plus infinity x of n z to the power minus n. Okay, we'll compare the general equation and this equation, and here instead of variable n, I'm using m. So there is no change with respect to the equation. So I can apply the definition of z transform. Therefore, the y of z is equal to z to the power minus n naught into x of z. So this is about time shifting property. And here, for example, if I'll consider x of n minus 2. So input signal is delayed by 2 units here, and z transform is what? Z to the power minus 2 into x of z. And if I'll consider x of n plus 1, and its z transform is what? Z into x of z. Or if I'll consider x of n plus 3, then its z transform is z to the power 3 into x of z. So it's very much useful in while solving the problems related to while solving the differential equation. We'll use this. So this is about time shifting property. So Third property we'll discuss scaling in Z domain. Scaling in Z domain, or it is also equal to the multiplication by exponential signal. And here, to prove this, if x of n its Z transform is x of z, then the y of n will consider alpha to the power n into x of n. So multiplying by an exponential signal, here alpha to the power n into x of n. Its Z transform is y of z is equal to x of z by alpha. Z by alpha. And the ROC of x of n is r, and the ROC of y of n is alpha into r. So you multiply by a constant term alpha. So generally the alpha you will consider as less than 1 here. Now applying the definition of the transform, we can write y of z is equal to summation of minus infinity plus infinity y of n into z to the power minus n. What is y of n? Y of n is alpha to the power n into x of n. So apply the definition there. Therefore, summation of n is for minus infinity plus infinity alpha to the power n x of n z to the power minus n. Now, summation from n is for minus infinity plus infinity x of n. Take n as common term, so alpha inverse z to the power minus n. Alpha inverse z to the power minus n. Now, again, we'll compare this equation with the general equation of the transform, that is x of z. So x of z, you know that it's a transform is x of n, it's a transform is x of z, it is n is for minus n plus infinity x of n, z to the power minus n. So instead of z, here you are having alpha inverse into z. Right? So therefore, instead of z, I write it as alpha inverse z, that is x of alpha inverse into z, it is equal to x is equal to x of z by alpha. Here alpha is the scaling factor. Alpha is a scaling factor, and that's what the property is called as a scaling in z domain. If I multiply with some exponential signal in a z transform, it's like a scaling. Scaling means just like multiplication, and based on that the signal will either be compressed or expanded. About the third property of Z transform. So next we'll discuss about time reversal. So time reversal, you know what is time reversal? The time reversal we discussed in the module 1. There, suppose x of n is input signal, and its time reversal will be given by x of minus n, that is replacing n by minus n. So the signal will be folded. Consider what is the transform of x of minus n. Now, to prove this, first we will define it. So if x of n, its z transform is x of z, then y of n is equal to x of minus n. Z transform is y of z is equal to x of 1 by z, or x of z inverse. Here ROC of x of n is r, and the ROC of x of minus n is 1 by r. To prove this, I will use the definition of Z transform. That is, y of z is summation n for minus infinity plus infinity y of n z to the power minus n. Right, y of n is equal to x of minus n z to the power minus n. Put minus n is equal to n. So you can observe the changes in the equation there. So now the limit changes, so minus infinity will become plus infinity, and plus infinity becomes minus infinity. So n is from plus infinity to minus infinity, x of n z to the power n. And if I interchange the limits in the summation, because the summation will add either from left to right, or it can add from right to left, effect will be same. So there is no change with respect to the answers. If I interchange the limit, because I'm not changing the sign here, just interchanging the limit. So interchanging the limit again. So n is for minus into plus infinity, x of n. I write z to the power n as z inverse to the power minus n. Correct, right? So here z to the power n can be written z inverse to the power minus n. Minus and minus get cancelled, so you get z to the power n. Now again, comparing with the standard form of Z transform equation, here Z is replaced by Z inverse. So therefore I'll write this as x of Z inverse. So x of Z inverse can be written as x of 1 by Z. So this is my y of Z. This is called as the time reversal property. So in the time domain, the next, if I suppose the n is replaced by minus n, that is x of minus n. In the z domain, it will be a z, with the inverse of z, that is x of 1 by z. About reversal property. The next property is convolution. So convolution in time domain is equal to multiplication in z domain, and this convolution concept we discussed in module 2. So they used convolution sum, and for convolution require two signals, and that is x of n. There I used x of n and h of n. So x of n star h of n will gives you output y of n. Generally the impulse response representation of a signal, and for discrete time signal we will call it as convolution sum. And here the property is convolution in a time domain, so I'll use star operator there, and it is equal to multiplication in a z domain. And as I mentioned, it requires two signals. So I'll consider two signals are x of n and y of n. If x of n its z transform is x of z with ROC is R1, and y of n its z transform is y of z with ROC is R2, then I'll take C of n is equal to x of n convolved with y of n, that is x of n star y of n. Z transform is C of z is equal to x of z into y of z. Convolution in time domain is equal to multiplication in a z domain. To prove this, is a definition of z transform, that is C of z is equal to summation over n is for minus n plus infinity, C of n into the power minus n, less C of n as x of n star y of n z to the power minus n. I will apply the equation for convolution sum. So you know that the convolution sum will be given by, and the two signals are here x of n and y of n. The convolution will be given by, this your C of n will be given by the summation over k is for minus infinity plus infinity x of k into y of n minus k. So performing the convolution between x of n and y of n here. So the same thing I'll substitute in the equation. So now summation over n is for minus infinity plus infinity, and then a definition of convolution sum here, that is k is for minus infinity plus infinity x of k into y of n minus k into z to the power minus n. Now I'll interchange the summation, interchange the order of the summation. So write k is for minus infinity plus infinity into x of k into summation over n is for minus infinity plus infinity y of n minus k into z to the power minus n. So next put n minus k is equal to m. So you'll get n is equal to k plus m. Now apply the limit here. 10 is minus infinity, so m is minus infinity, and put n is plus infinity, m is also plus infinity. There is no change with respect to the limits, lower limit and upper limit. I'll substitute in the equation, so we'll get summation of k is for minus 1 plus infinity x of k into summation where m is from minus infinity plus infinity y of n to z the power minus of k plus m. Now while rearranging this, again summation of k from minus infinity plus infinity x of k into summation of m is from minus infinity plus infinity y of m. I expand it is z to the power minus k into z to the power minus m. And I will take z to the power minus k is constant because the second summation, the variable I am using is m. So I will take it as take the term as a constant. So I take it outside. So I can write it as k is from minus infinity plus infinity x of k into z to the power minus k into the summation m is from minus plus infinity y of m into z to the power minus m. I will use the definition of z transform, that is c of z is equal to x of z into y of z. And this is about the convolution property. So it's very important property in the Z transform, that is convolution in a time domain is always equal to the multiplication in a frequency domain or Z domain. And so while solving the problem also, the two signals and take the convolution of that, and in the Z domain it will be just a multiplication. So performing multiplication operation will be easy compared to the convolution operation that we discussed in the module 2. Next we'll discuss about differentiation in Z domain. There's also multiplication by a ramp signal. So you know that what is ramp signal? The ramp signal generally given as R of n, that is equal to n, and its value is n for n greater than or equal to 0 and 0 for n less than 0. So ramp signal. So in time domain we'll consider it as a ramp signal. In the frequency domain or in the Z domain it will be a multiplication. So sorry, it will be a differentiation. So define it, and if x of n its Z transform is x of z, then n into x of n its Z transform is minus z d by dz x of z. So on the left hand side you are having multiplication by ramp signal, and the right hand side you are having differentiation in Z domain. I'll use the definition of Z transform, that is x of z is n is from minus infinity plus infinity x of n into z to the power minus n. Differentiate with respect to z. So d of x of z by dz is equal to the summation of n from minus infinity plus infinity x of n d by dz of z to the power minus n. Next step is the summation is from n over minus infinity plus infinity x of n. The differentiation of z to the power minus n is minus n into z to the power minus n minus 1. Next I will expand that term, so I will get minus z inverse, and the summation of minus infinity plus infinity x of n into n z to the power minus n. Now rearranging and simplifying the equation, I will get the minus z into d of x of z by dz is equal to the summation over n is from minus infinity plus infinity x of n into n z to the power minus n. And you will consider that n into x of n as a single term, and then I'll compare with the x of z equation there. So instead of x of n, here n into x of n. Therefore I'll write it as minus z d of x of z by dz is equal to the z transform n into x of n. Therefore the multiplication by ramp signal results in a differentiation in a Z domain. These are the properties of Z transform. So we have discussed about the linearity property. So for the linearity property, and it should satisfy the law of superposition. They will consider more than two signals, and the weighted sum of input should be equal to the weighted sum of output. And the ROC also will define that the ROC of first signal is R1 and ROC of the second signal is R2, and the ROC of the resultant signal is intersection of R1 and R2. So the linearity property. The second property we discussed is the time shifting. The time shifting means we'll consider the signal as x of n, and we'll take the shifted version of the signal. It is x of n minus n naught, and its Z transform is z to the power minus n naught into x of z. So the shift in the time domain results in a multiplication by constant in the z domain, the complex term, that is z to the power minus n naught. And as I mentioned, the time shifting property commonly used to solve a difference equation, and to solve LT systems, and we'll use that. Then we discussed about the multiplication by exponential signal is equal to scaling in Z domain. So we multiply to the exponential signal, and it results in scaling in Z domain, that is alpha to the power into x of n will be x of z by alpha. And the fourth property we discussed about the time reversal. Time reversal means we take the reflected version of the input signal, that is x of minus n. In Z domain it is x of z inverse, or x of 1 by z. With respect to the ROC of x of n is r, and the ROC of x of minus n is 1 by r. And the property we discussed about the convolution. And the convolution, and as I mentioned, it is a discrete time signal, so we use the convolution sum here. So the convolution also requires two signals. So convolution property states that the convolution in time domain should be equal to multiplication in a Z domain. So consider the two inputs as x of n and y of n. That is x of n star y of n. The star indicates convolution operator. In the Z transform, it is x of z into y of z. That is in the Z domain. And with respect to the ROC also, the ROC of the x of n is R1, and the ROC of y of n is R2, and the ROC of resultant signal is R1 intersection with R2. And on this convolution property also, we'll use a convolution property because it will be very easy to multiply the two signals instead of performing convolution operation, because to analyze any system or to solve discrete time system or LT system, it's very easy if I use a Z transform instead of using time domain technique. If I'm using a frequency domain technique, it will be very easy. It is an advantage of using the frequency domain technique or Z domain technique here. The last property we discussed about differentiation in Z domain. So differentiation in Z domain, and here that is also equal to the multiplication by a ramp signal. So ramp signal, what is the ramp signal? Ramp signal is given by n. Its value is n for n greater than or equal to 0 and 0 for n less than 0. And in the Z domain, it is a differentiation. So multiplication of a ramp signal results in a differentiation in a Z domain. That is minus z into d by dz of x sub z. So the ROC, there will be no change with respect to the ROC of x of n, and you When multiply the ramp signal, there is no change with respect to the ROC of the signal. So by using these properties, we'll solve different problems. By using the properties, so solve different problems. Like we'll give x of n, and you have to apply the properties, either a linearity property, time shifting properties, or a time reversal property, differentiation in Z domain, convolution property, and all. You can solve different type of problems. And if I know some of the transform of some standard signal, that is u of n, then delta of n, alpha to the power t of n, then directly you know what is the transform of alpha to the power t of n. The transform alpha to the power t of n is z by z minus alpha. Then the signal I want a shifted version of that, x of n minus 2, then I just multiply with the power minus 2. Okay, similarly you can use different properties and apply the properties for the standard signals and obtain the Z transform. Similarly, while taking the inverse Z transform also, it will be easy because Z transform pair will be there, that is x of n and x of z. The x of z will be given, and you have to obtain x of n. So there also will apply some properties of Z transform and will solve the problem. So that is an advantage of using properties. Thank you.